What's up, geeks, and welcome to the channel. Couple of months back, this series was constantly being enriched with several uploads explaining trees and its several implementations. And after going over binary search trees, graphs, maps, and multiple traversal techniques, today it is finally time we tackle tries. So, a trie, also referred to as a prefix tree, is a type of search trees usually used to store strings in order to optimize the search complexity or the retrieval of these strings, which means that we will be able to retrieve the strings we stored in a faster manner. But how is this tree created? You see, the tree takes a string, or a word if you want, as a parameter, and then creates a new node for each character of that word. The node registered for the last character of the string or word is marked as the end of word. If we try to add a couple more words to this tree, you will see that if they share the same prefix, the characters they share are not reinserted in the tree, but the already present characters or nodes are used instead. And all of the words we inserted share the same root prefix, the empty character string, and hence the name prefix tree. Okay, we mentioned that this tree optimizes the lookup of these words. Let's see how. To do that, suppose we want to look up in the tree you see the word like. So we start at the root and hop to the node containing the first character in the given word. If the next character is present among the children of the character we are standing at, then we keep iterating, or else we conclude that this word does not exist in our tree. You see, to find a word inside the tree, we didn't have to traverse the tree itself, using, for example, depth first or breadth first search. A traversal was never needed because the path that we had to follow was provided by the input itself. And this traversal was done in an O of n time complexity, n being the number of characters in the input. Now you might be thinking that we are the ones who inserted these words inside the tree in the first place, so why would we need to search for them, right? Well, the most common examples and usages of such trees are autocomplete and predictive text. You see, as soon as you start typing, algorithms behind the scene will be running a tree such as this one, and will try to search for a matching prefix to the one you are typing. The words that are suggested to you are none other than the words branching from the same prefix you gave to the tree. Another application of this tree, like other trees, could be to use it as a map with string as its keys. So, instead of only marking the end of the word with a boolean, for example, we can mark it with any actual value. This way, the string leading to the value will be the key of the entry in this map, and the data marking the end of this word will be the value corresponding to that key. Okay, now that we know how to construct a prefix tree and look up a string inside it, let's go ahead and implement these functionalities along with a few extra operations in which these trees excel. As with all the trees we covered, and before jumping into the actual implementation of these operations, let's take a look at the node class, which will represent the nodes of our tree. This class will store a character, of course, and a map of the children of this node. We chose to represent the children using a map and not a list here, because it will be easier and faster to retrieve a specific child based on the character using the map instead of looping over a list. Additionally, do not forget to add a boolean to specify if this node represents the end of a particular word or not, as we mentioned previously. Now that our node class is complete, let's take a look at the tree interface we will be implementing in a few. As you can see, in addition to the traditional insert, contains, and delete operations, we will be implementing two additional functionalities: the contains prefix and the words with prefix functionality. Now on to our main class implementation. Concerning the trie class, it will have a single attribute, a node, which is the root node of the tree. This node will be initialized in the constructor as the empty string, exactly as we mentioned earlier in the video. Now, for the insert operation, it will take a word as a parameter, and for each character of that word, we need to check if that character is already present in the tree we have, in the order they figure in the word. So, suppose we have a tree with the word like, and we want to insert the word life. For the code we wrote, L is the child of our root, and I is the child of L. So the if condition we wrote will return true for the first two iterations. However, for the third one, the else block should be executed, and what we need to do here is create a new branch for this word. To do that, in the else block, we need to initialize the current node variable to a new node containing our new character, and then this new node will be added to the set of children of the last common character we encountered. Now, you may be wondering that both these calls are part of the iteration over the tree. But why is the current node variable iteration restricted to the if statement, and the children iteration is outside the if statement and being executed in both cases? Well, even if we didn't find a match, this call will ensure that the children variable will get initialized to an empty map to be filled later in the put call. But not an empty map, the map referencing the children of the newly created node. This way we ensure that the link between all our nodes is maintained and remains unbroken. Finally, don't forget at the end, after the loop is over, to set the end of word boolean value to true as we reached the last character of the word. Okay, now that we implemented the insert operation, let's implement the contains functionality. To do that, I will make use of a helper method, the search method, and you will see why in a few. Inside this method, we will use a very similar approach to the one we used in the insert operation. We will keep iterating over the characters of the string while keeping track of the current node and its children. However, as soon as we don't find a certain character, we will return the null value, because our target here isn't to populate the tree, but instead make sure that a certain word exists inside it. And on the other hand, if we do find a match for our string, what we are going to do is return the last node corresponding to this match. Now back to our contains method, where we will check if the returned node is not null, of course, and if it is, we will check if it is marked by an end of word, because if it is, then the word passed to the method indeed exists in our tree. Okay, you may think that the implementation we did is a bit weird, like why not return true or false directly from within the search operation? Well, it is because we are going to use this method for several other functionalities. The first one being the contains prefix functionality. All we have to do here is call the search method and return true if the node we got is not null. We don't need the string passed to the method to be a full word in this case, just a prefix. Another use case could be to return a list of the words having a certain prefix. To do that, we have to first check if this prefix indeed exists, and retrieve the last common node of this prefix, which is what the search method we just implemented actually does for us. Then, if this node is not null, what I did was made use of recursion to generate the list of words using this addWords method. What this method will do is iterate over the children of the given node, and for each child it will re-invoke the same method on the concatenation of the prefix and of all the characters we have up until that character. The recursive calls will stop when we hit a node with the end of word boolean set to true. At this stage, the resulting word will be added to the list of words we are forming and will be returned to the user. Okay, finally, the last operation we are going to implement is the delete operation. To delete a certain word from a prefix tree, the first thing you need to do is of course loop over the characters of the word to delete while keeping track of the children of each character. Now, every node belonging to that word should be stored in a list, as we will later check if it is eligible to be deleted from the tree or not. We'll get to the whole eligibility part in a bit, don't worry. Additionally, make sure to add in your loop a breaking condition, which ensures that as soon as the characters of the word we want to delete are not found in the tree, the operation aborts, as we cannot delete something that doesn't exist in the first place. Now, after this loop ends, we need to make sure that the list we filled is not empty, and that its size matches the number of characters of our word to delete or its length. Because if that's not the case, we need to exit the method as well. Okay, at this point, if all is fine, what we need to do is set the end of word boolean of the last node to false. And that's how you delete a word from a prefix tree. Everything that follows is just cleaning unnecessary nodes. Because you see, if we had something like that, and we want to delete the word geek, for example, we can't delete the actual nodes, as the word geekific relies on them too. So in this case, removing the flag is more than enough. But how and when do we want to remove non-needed nodes? To do that, we have to loop over the nodes we have, in reverse order. And for each node, we have to check if it has any other children that rely on it. If it doesn't, then it is safe to remove it from the list of nodes linking it to its parent node, which is the previous node or the i-1 node. So, if we had a tree with like and life as its nodes, and we want to delete life, this condition prevents us from deleting the characters L and I, as like also relies on them. The last thing we need to do here is check if the node we have is marked by an end of word. And if that is the case, then we have to break out of the loop. Why is that? Well, let's go back to our previous example and suppose we were removing geekific instead of geek. We will start by setting the end of word boolean to false on the character C. Then go inside for the loop and delete the C, then the I, then the F, then the second I. When we reach the letter K, we will check if its children's map is empty. And well, yes it is, we just deleted the last child. So if we didn't have this last check, we will go ahead and delete the node K all the way till the root. The last condition we added prevents this from happening. Now, before ending the video, I want us to visualize and test this implementation together. To do that, I created a main class and inserted a bunch of words into the tree. If you are familiar with the tree view class, or if you've watched our trees visualization video, you may recognize the piece of code we just added. When we run it, we are going to obtain the tree you see in front of you, which reflects exactly what we've been discussing since the beginning of the video. Finally, if you try to delete a string from the tree and rerun the code, you will see that the word in question was indeed deleted correctly. So, that's it for this video. I hope it was helpful. Thank you guys for watching, take care, and I will see you in the next one.